when you're adding the sum of all your terms of an infinite series, you have an infinite number of terms. And as you're talking about an infinite number of terms, you automatically think, well, if I have an infinite number of terms, if I add the next one, it's just going to continue to get bigger and bigger and bigger. And that's the idea of the word divergent. When you're talking about divergence, your sum continues to get bigger and bigger and bigger. As you add another term, the sum of those terms continue to get bigger and bigger and bigger. When you have an arithmetic, that is true. When you have a geometric and your absolute value, your ratio is greater than the value 1. That is the idea of divergent. But if your absolute value of the ratio gets smaller than the value is smaller than the value 1, this converges on a specific number. And as we talked about yesterday, when we're talking about geometric sum, the geometric sum, n is your term number, and n will continue to get bigger and bigger and bigger. If your ratio is between -1 and 1, if it is a decimal, and you take it to a larger and larger exponent, the number will get smaller and smaller and smaller. So eventually this will go to a value of 0. As n gets closer to infinity, r gets closer to the value 0. So we're left with 1 minus 0, which is a value of just 1. So I have T1 is equal to 1 minus the value of R. And this is the sum of an infinite series, geometric series with absolute value of the ratio is less than the value of 1. You had a worksheet that dealt with infinite series, and you also had some factorials on the back, questions you have on the factorials or infinite series. Yeah. Number 8, you have Tn is equal to 1/4 Tn minus 1. T1 is equal to negative 512. If we take a look, if we're in the form Tn is equal to 1/4 Tn minus 1, T1 is equal to negative 512. Okay, we take a look at this form. This is a recursive formula for a geometric series. This is a recursive form for a geometric series. And my ratio is a value of 1/4. So my absolute value of my ratio is less than the value of 1, which means I have an infinite geometric series. No, I'm sorry, I see what that. I have S10 there rather than S infinity. All right. And I ask you for S10, that should be an infinite series then. So it should be S infinity rather than S10. So we take our first term. Our first term is negative 512. And 1 minus 1/4 on the bottom, which is 1 minus, or 3/4. It should be an S infinity rather than an S10 in infinite series. My mistake. Can't be perfect all the time. Other questions you have? Factorials? Hopefully you yelled as you did them. Hopefully in your brain you sat there and went, that was 7 divided by 10. All right, today we're going to deal with repeating decimals. Working through repeating decimals. And we're going to take a look at making a repeating decimal, changing it back into a fraction. Your definition of a rational expression, a rational fraction, a proper one is two numbers divided by another. You have anything that could be put into a fractional form. Anything that could be put into a fractional form would be two numbers, one divided by a second number, a divided by b, where a can be any number, any whole number, or any integer. B can be anything but a value of 0. B cannot equal 0. A is any integer. And these are both integers. Once again, B cannot be a value of 0. Anything in the form of A over B, B cannot equal 0. Well, when we're talking about a fraction, any proper fraction can be converted into a decimal that's either going to terminate or repeat. Any fraction can be converted into a decimal that will either terminate or repeat. Which means we should be able to change any decimal back into a fraction or a rational expression. Once again, the key to mathematics, and the nice thing about mathematics, is every process is doable in the mathematic world, is undoable also in that mathematic world. Well, if I had the fraction or the decimal 0.3, and I want to change that into a fraction, 0.3 as a fraction would be what, Grayson? 3 over 10. 0.27 as a fraction would be what, Jack? 27 over 100. 0.213 as a fraction would be what, Kylie? And what we learned back in 5th and 6th grade math, when we was able to start dealing with the idea of decimals, is the number of decimal places we had tells us the number of zeros that go on the bottom. 0.3, I have one decimal place, so I have 1 0 on the bottom. 10 and 1 and 1 0. 0.27 has 2 decimal places. Tells me to put 2 zeros in the bottom, 1 and 2 zeros. 0.213, I have 3 decimal places, so I'm going to put 3 zeros in the bottom. 0.3217, how many zeros are going to go on the bottom? Quentin? 4. And it allows us to convert a decimal back into a fraction. But the question is, what happens if I have 0.3 with a bar above that? What the bar means is that I have a 0.33333, and so on. I have an infinite number of decimal places, which means in the denominator, I'd have an infinite number of zeros, which sort of is a problem because I cannot write a proper fraction as 3 with this and 1, 0 with that and say that's a proper fraction. Or I'm going to just continue with my zeros and continue with my 3s. Not a proper fraction. Well, we've been through enough mathematics, and hopefully we can say, well, if I have 0.33333 and so on, what is that fraction? What's the fraction? 0.3 repeating. Ooh. Math knowledge. 1/3. Yeah, 1/3. If I have 1/3, that's going to come down to 0.3333 and so on. And I can prove that by just putting it in my calculator. 1 divided by 3 is going to throw me out a bunch of 3's there. 0.3333. So that is our math knowledge. Well, what if I have 0.17 though, and I want to change that into a fraction? That becomes an issue. So let's go back to the 0.333 again. What we are trying to create is we're trying to create a fraction this fraction n. We're trying to create this fraction n so it equals 0.33333 and so on. Now there's two ways to skin the proverbial cat. We can look at the idea of a geometric series, an infinite geometric series. I don't like that as much because I think this is sort of cool. This is a little bit easier to work with. I don't have to throw the idea of geometric series into this. I could just use my mathematical knowledge and solving equations to be able to solve this. I'm letting n be that one fraction that equals 0.333 and so on. And what we're going to use is we're going to use a multiplication property, the multiplication property of equality, which allows me to multiply both sides of the equal sign by the exact same thing and not change the equality. If I multiply both sides by 5, I multiply n by 5 and 0.333 by 5. I'm not going to change my inequality or my equality here. Well, what I'm going to want to multiply by is I'm going to choose the value of 10. If I multiply both sides of this equal sign by 10, now don't get too antsy here, because what I'm going to do is I'm going to put it above. I'm going to multiply n by the value of 10. We're left with 10n. That's going to equal to the right-hand side multiplied by the value of 10. Well, when I multiply a decimal by 10, what does that do to my decimal point, Courtney? Yeah, it moves it over. So if I multiply the n by 10, I get 10n. If I multiply 0.3333 repeating by 10, I get 3.3333, and so on. All it does is it moves my decimal point over one position. That's why we multiply by 10. I can pick any number I want here, but 10's a lot easier, because when I multiply decimal by 10, it just moves the decimal point over one spot. If two things are equal, if this is equal to this and this is equal to this, I have equality here, I have equality here. If we would subtract equality from equality, I'm going to maintain equality. If I subtract two things that are equal from two things that are equal, I'm still going to get equal things. On the left-hand side, I have 10n minus n, which gives us what, Todd? 10n minus n, what do we get? 9n. Okay, something we've been able to do in algebra The cool thing is when I subtract over here, what happens to all the 0.33333s and so on? They go adios. These all cancel. No matter how many there are out there, which means there's an infinite number of them, they will all cancel, leaving us with just the value of 3. Now, solving this equation, we can divide by 9, divide by 9. N is 3 divided by 9, N is equal to 1/3. Let's look at 0.17 repeating, which is 0.1717171717, and so on. We want to find the fraction n that equals that 0.1717171717, and so on. If we would follow the same method of madness, multiply both sides by 10. We would have 10n is equal to, if I multiply the bottom by 10, it moves my decimal point 1 position. So we have 1.71717171, and so on. The problem we run into is when we would subtract here, do all those infinite decimals cancel out? No, they don't. I have 7 minus 1, I have 1 minus 7, I have 7 minus 1, so they don't cancel out. So following that same method of madness does not quite work. So multiplying by 10 doesn't work. But what can I multiply by? What could we multiply by to create the exact same thing that just occurred before? Lexi, what do you think? 100. Let's try 100. So if I multiply both sides by 100, we have 100n here. If I multiply 0.17, a decimal, by 100, how many places do we move the decimal point? Multiply by 100, how many places do we move it? Justin? 2. So I'm going to move my decimal point 2 positions. So we're left with 17.17171717, and so on. Now when we subtract, over here we get our 99n. On the right-hand side, do we get our decimals to cancel now? Yeah, they all go bye-bye, leaving us with just 17. Dividing both by 99, n is equal to 17 divided by 99. Now, we could check this easily in our calculator. Does 17 divided by 99? What do I come up with? Do I come up with the 0.17171717, so on? So what we're able to do is we're able to look at taking a decimal that is a repeating decimal and move it back into a fraction. We've always been able to take a terminating decimal into a fraction because that just tells us how many zeros. The number of decimal places tells us how many zeros. Take a look at another one. 0.13 repeating. Now the only decimal point, the only decimal place that's repeating is just the 3. Now, if we multiply both sides, go back to what we did at the beginning, it's multiply both sides by 10. If we multiply both sides by 10, do we have matching of decimals that will cancel? Let's see what happens if we multiply both sides by 10. We have 10n here. This is going to move my decimal place one position. So we have 1.33333, and so on. We have on the left-hand side 9n. On the right-hand side, well, I have 1.3 and I have a 0.1 there. That doesn't match up, but does all my repeaters cancel after that? Yeah, these cancel, these cancel, these all cancel. So we're left with 1.3 minus 0.1, which is 1.2. Dividing both sides by 9. Dividing both sides by 9. I have 1.2 divided by 9, which is not a proper fraction. Because a proper fraction is a divided by b. A's and b's are both integers. B cannot equal 0. So we need to be able to convert our decimal, our fraction here that's improper, into a decimal. Well, using equivalent fractions, what could we multiply top and bottom by to move my decimal point over one position? What can we multiply top and bottom by? 10. So if we multiply top and bottom by 10, what we are left with is 12 over 90, which we can reduce down by taking 6 out of top and bottom. So we have 2 out of 15. If we take 2 divided by 15, in our calculator, 2 divided by 15, do I get 0.1333333 and so on? Yep. So sometimes when they don't quite match up, you might have to do some additional work. Well, let's look for some patterns here. Let's look for a rule of thumb, and it doesn't matter if it's a left or right thumb that we can utilize. Okay, and let's go back one more step here. If I decided to multiply by 100 here, I can get the same result here. Okay, the numbers just get a little bit bigger. But if I take a look, when I had 0.3 repeating, I multiplied both sides by 10. When I had 0.17 repeating, I had to multiply both sides by 100. When I had 0.13, just the 3 is repeating, I was okay with multiplying both sides by 10. Well, what would be a rule of thumb that we can utilize to determine what are we going to multiply both sides by? What do I multiply both sides by? I want to be able to move my decimal point over. Okay, the number of repeaters you have. The number of repeaters that you have, that's what you can multiply top of, or both sides of the equal sign by. So in the first one, I had 1 repeater, multiply both sides by 10, 1 0. Second one, I had 2 repeaters, multiply both sides by 100, 2 zeros. Third one, I had 0.133, 1 repeater, multiply both sides by 10. .124, the bar is only above the 2.4. So we have 0.124, 24, 24, and so on. Okay, the number of repeaters you have, 2. So it tells you how many zeros to multiply both sides of the equal sign by. So go ahead and multiply both sides equal sign by the zeros. Go ahead and put it above it. See, it's a little bit easier for you to do the subtraction. Looks a little kinder on your eyes. Go ahead and subtract down. So we have 99n is equal to 12 point, these two fours all cancel out. So we have 12.3 dividing both sides by 99. Then you have to put it into a proper form. You multiply top and bottom by 10 and then reduce your fraction down. Let's see, 1, 2, 3 adds up to 6. 990, 18, so it's divisible by 6, or I'm sorry, by 3. So we have 41 over 330. Now once again, you can easily check this by just clickety-clacking your calculator. What is 41 divided by 330? Do I come down to the 0.124242424 and so on? Go ahead and do the next 3 and check your answer with somebody around you. Second one here, Sophia Carpenter, what do you come up with?
314 over 99.
Anybody convert that back into a decimal? 214 over 99? Anybody convert it back into a decimal? Or I'm sorry, a mixed number. If you convert it back into a mixed number, that would be 317 over 99. Second one, Brandon Shannon, what do you come up with?
2 over 15.
2 over 15. And the last one, what do you get, Owen? All right. Questions you have on repeating decimals? Okay, the homework, which was a worksheet that we have on the back, we just did your homework. So we have completed that. So you have nothing for tonight. Tomorrow we'll come in, we'll deal with some sigma, start working through some ideas of sigma, and that will be the last of our material. That will take a few days to be able to get through it, though. Once again, I'm looking for a quiz sometime towards the middle of next week, then next week, and we'll be able to complete what we need to complete here. Questions you have? QED as done.